Hello and welcome to today's webinar presented by Dlubal Software. Today we'll be working in our structural analysis and design software, RFEM. The topic for today's webinar is plate and shell modeling in RFEM Part 1. My name is Amy Heilig. I'll be the presenter. I'm the CEO of the U.S. office and also a technical support and sales engineer, and we are located in Philadelphia, Pennsylvania. My colleague Alex Bacon will be your moderator, answering any questions you may have. He's a technical support engineer, also located in our Philadelphia office. If the control panel does seem to get in your way when you logged into this GoToWebinar, feel free to show or hide that with the orange arrow up at the top. I always want to encourage everyone to ask questions throughout the presentation. You can do so within the same dialog box. If by chance we don't get to all your questions, we will certainly send you a follow-up email afterwards. So regarding the content for the next hour today, this will be an introduction into our finite element analysis program, RFEM, for plate and shell modeling. So this is part one of a two-part webinar series. Today, we're really going to be focusing only on the modeling of the tank structure, which you can see over on the right-hand side. We're going to discuss certain aspects such as the FE mesh settings and mesh refinements. We will set up our load cases as well as our load combinations per the ASCE 7. And finally, we will apply the loads to the structure. So we won't necessarily be getting into any of the analysis and the design results for our webinar today, but rather that will be covered in the second part of this webinar series. So not to spend too much time here on the introduction, what we can do is to launch our program RFEM to get started with the example today. We do want to first give the model a name, so we can title this one Plate Webinar. The type of model is a 3D. We want to orient the global z-axis in the upward direction, and if we expand these detailed settings here, we can also set the local axes of both our surfaces and members to the downward direction. Now this is default and this is suggested mainly for concrete design, which isn't so important for today. We are going to generate the load combinations automatically according to the ASCE 7 2016. You can see here we have the NBC standard available to us as well as many other international standards. We also can click this button over here that will allow us to access some of the older standards not directly available within this drop-down box. When we check this checkbox, the load combinations will automatically be generated by the program. In turn, we can uncheck this option here and that will allow us to manually create our load combinations instead. So perhaps we wanted to import in all load combinations from Microsoft Excel, for example. Today we'll be taking advantage of the load combination generator, and we can click OK, and we're immediately brought into our main program, RFEM. Now, not to spend a significant amount of time here either, just giving you a brief introduction into the program. We have our graphical interface here in the center. So as we begin to model the structure, of course, we'll be seeing that right here within the graphical window. We have our tables to work with down at the bottom, and I actually will touch on this today. We can essentially input all of our input data for the model within this table as well, rather than graphically drawing everything. We can import in directly from Microsoft Excel. After we run an analysis, which we'll see within RFEM, the second part of this series, we can also export all of our result data to Microsoft Excel from the program here. We have our quick tools up at the top, which we'll certainly be utilizing today. These are customizable. You can add additional tools. We have our drop-down boxes up at the top. And then over on the left, we have our project navigator. So as we begin to generate this model, all of our input data will be available over on the left-hand side here. So we can make quick changes to materials, to surfaces. We also have all of the add-on modules listed within the Project Navigator. So the add-on modules we will not be touching on today, but we'll see this again in that second part series. So to begin with, I want to start off by drawing a new node. Now, typically I would go up here to draw a new node within these quick tools, and I could snap to any portion within my graphical window here. I can type in the XYZ coordinates, but rather what I'd like to do is to actually input the data directly here within the model. And before I do, I want to take a look at the units and decimal places, because today we're going to be working with something a little bit outside of what the default is. Now, you'll notice that we can either set the default here as imperial or metric. So typically I'd set my default to imperial. Now, to change the actual dimensions of my current model that I'm in, what I need to do here is to double click. So you'll notice currently the model is set in metric. If I double click on imperial, everything is set correctly according to imperial. Now for my lengths, I want to give this an adjustment to inches instead, and I'm going to change this to 2 decimal places. So rather than the default of feet, we'll use inches for today's example, and I click OK. So now when we want to go in and type in our coordinates for our nodes directly in the table, you'll notice here I can type or put my cursor within the first cell. Then this allows me to simply type in the X, Y, and Z coordinates. So we'll start off with 0, 0, 0. The next coordinate will be 0, 0, 42 inches in the Z. The third will be 0, 0, and 70. So you'll notice these nodes being generated here in our graphical window as we type them in. Now I have 3 more nodes here I want to input at 16.8, 0, and 66 inches. 19.2, 0, and 63 inches. And finally, my last node will be 19.2, 0, and 42 inches. So here are these nodes displayed in our graphical window, and I can move this table down. And they don't really mean too much right now, but what we want to do is to connect these nodes with line elements. And for this, I will go to the option up here in my tools to draw a new line. The first line segment will just be a simple straight line where I'm going to connect this bottom node to this top node. But my next line element, I would actually like it to be an arc. So we have the ability here to define an arc, and I can select from one node to the next. Now, currently this is in the correct orientation here for defining my radius. But if we saw that the radius was being defined into the page here, all we need to do is just to adjust the plane, local, and Z. Then I can simply type on my keyboard the radius of 5 inches. I hit enter, and now we see a slightly curved line here. I'm going to do the exact same concept to connect these 2 points with an arc, and I'm going to set the radius to 40 inches, and I hit enter on my keyboard. I right click out of this, and now you can see kind of the beginning outline here of the top of our tank structure. I'm going to take all of these elements and highlight them within my selection box, and I'm going to utilize what's called the mirror tool. And the mirror tool is exactly as it sounds, maybe similar to something that we would find in AutoCAD, where we can create a copy, and we'd like to mirror about the X, Y plane. Then we need to select the mirror point location. So for this, I can graphically select this node. You can see the point coordinates are automatically filled in. I click OK, and now I have a mirror for the representation of the bottom portion of my tank. I'd like to delete this node here, but if I simply highlight it and hit delete on my keyboard, these additional line elements are also going to be deleted. So what I can do instead is to right click here, and under delete node, I have the ability to merge the joined lines. So when I do this, you'll notice that I have a single line element here. Okay, so with all of these line and node elements, I'm going to highlight them together, and we're going to use our rotate copy tool. With the rotate copy tool, I want to make 3 copies at 120 degrees. I'm going to rotate about this center point here, 0042. But in addition to this, if I expand my detail settings here, this little magnifying glass, I then have the ability to create surfaces between my copied lines. So when I click OK through all of these dialog boxes, you'll notice that my surfaces were automatically generated. Right now they are this red color, and the reason why is because if I highlight all of them, I double click to edit, the stiffness is set to null. All we need to do is to change this to standard stiffness and to define a material and thickness. Now, typically when you first start the program, the default materials you might see would be steel A992 and concrete 4000 PSI. So rather, we'd like to access our material database. We can use our filters over on the left to filter to metal, for example. Under the next drop-down, we have steel, stainless steel, aluminum, and so on. For today, I want to utilize stainless steel, and in particular, A240. Well, this is a very long list, so we can take advantage here of the search options where I just type in A240, and now you can see my list is a little bit shorter. We also can utilize what's called the favorites group. With the favorites group, we can create a new favorites group or edit an existing group. And this allows me to simply turn on and off these check boxes. I can maybe change these filters over on the left to add maybe a handful of materials that I use quite often for all of my projects. That way I'm not filtering through this long list every time I'm generating a new model. So for example, I added the stainless steel material that I'd like to use for today's webinar. All my material properties are given to me here. Keep in mind that if you don't find your material, no problem. You can always create a new material. You just simply give it a name, you categorize it in one of these drop-down boxes, you input in the material properties, you click OK. It will then be saved into your material database for all future projects. So we are going to utilize stainless steel A240. I need to set the thickness here for the body of my tank to 0.2 inches, and I click OK. So now we no longer have this red color, but rather we have this steel kind of purplish bluish color. So I'm going to move on to modeling the manhole, which is how we access the inside of the tank, of course, from the top. I'm going to put my view here in the reverse Z direction. So I'm now currently looking at the plan view of my structure from the top. I'm going to highlight only a particular segment here, and I'm going to create a user-defined visibility. Now you'll notice that the rest of the tank is grayed out, so I no longer have the ability to select it here. I can even take it a step further by right-clicking within the white space to turn off the hidden objects in the background. So I only have 1/3 of my tank body shown. Now, for the ease of modeling, you'll notice everything's at a skew right here from the global X, Y, and Z coordinates. This isn't exactly user-friendly when we're trying to model certain elements within these particular surface elements here. So what we have the ability to do is to create our own user-defined coordinate system. And it's very quick to do by selecting this tool up at the top, where we can choose a work plane with 3 points. So I'm going to choose my lower center point, my upper center point, and my third point is going to be on the outer center. Now you'll notice I've created my own user-defined coordinate system based on UVW axes here, and this will be extremely beneficial, which you'll see as we begin to model. So I'm going to take this top node here and select it and use my Move Copy tool. I want to create one copy, but I'm going to take advantage of that user-defined coordinate system, U, V, and W, rather than the X, Y, Z. I want to make one copy in the 12-inch direction of the axes W. I can see those axes right here. I want to go under my expanded settings to turn off the ability to create surfaces between copied lines. I click OK, and now we just kind of have this node floating up above the roof of our tank. I'm going to choose any arbitrary vertical line here, and I'm going to select it. I'm going to hold down my control key to select the top node. I continue holding down my control key, and I'm going to drag and drop to make a copy and attach it to that node that we just copied over. So all that we have now is just a general line element passing through the top of that roof. But the reason that I did that is because I want to take advantage of this Connect Lines or Members tool. When I select this tool and I hover over the surface and the line, you'll notice that the program will automatically generate a node where the surface and the line intersect, and this node will automatically be integrated into this top surface. We don't have to take care of any of that manually. So I'm now done with this top node, so I can simply hit delete, and I have my existing line element inside the tank. I actually want to rotate this 30 degrees. Well, once again, we'll access our rotate tool. I don't want to make any copies here. I want to rotate -30 degrees about those user-defined axes here. And for the user-defined axes, we're going to be rotating about the V axis. Then I need to choose my rotation start point, which will be up here at the top. I click OK, so now you can see I just have simply rotated that line 30 degrees. This will be beneficial as we continue to model this for our manhole. I'm going to right-click on this line, and we have the ability to extend it. To extend the line, I want to extend it by just a simple 2 inches. So this is essentially how far up my manhole is going to protrude above the top of this surface. I want to extend it on the J end. I know which end is the I and J because of the black arrow here showing me what's the line start and the line end, and I click OK. I'm going to right-click on the line again, and I'm going to divide the line by a certain distance. And I'm going to choose here 8 inches from the line end. Again, I have no confusion over what the line start and end is because of my arrow here. I click OK, and now I just have generated 2 separate lines here. I'm done with this lower line, so I just simply delete the node. And then I have my single line element rotated at 30 degrees passing through that top roof. So the benefit of this now is we want to kind of generate this manhole opening as well as some surfaces protruding up in the vertical direction about this line. And the easiest way to do this is to select one of the options within our drop-down box here. And actually, let me move over. We want to choose the option to draw a new pipe. The pipe option is just a way to automatically draw these surfaces with just a few input parameters. So we specify the material. We keep this as stainless steel. I do want to modify the thickness here to 0.4 inches. The second tab allows me to specify the radius of the pipe, which we will set to 8 inches. Now we have some other options in here where maybe we want to vary the radius along the length. We won't be getting into any of that today, but you do have the ability, you can change thicknesses as well along the length. So once I click OK, all I need to do is to click this line element. Now you can see that that circular surface is placed around that reference line. What I'd like to do now is to have the program automatically detect where these surfaces are intersecting. And I can do this by highlighting all of my surfaces that contain these intersections. I right-click under Surface and I choose the option Create Intersection. The program will automatically determine, even with this complex curve geometry here, where these two surfaces intersect. And from here, it will actually create separate components. And what we have the ability to do is to right-click on one of these components to deactivate it. So now I have a true opening down into the center of the tank. I can right-click on this additional component to deactivate it. We flip this around. I also want to deactivate the component on the inside of the tank. So now, of course, we have all of these nodes and lines shown, but just keep in mind that those are really only for modeling purposes. They're not going to add any stiffness or influence our analysis at all, but rather we just have this single surface protruding up here to represent our manhole with a clear opening down into the center of the tank. Okay, so now we have completed the modeling of the manhole. So I'd like to go back to our full view here by canceling my visibility mode. Let's turn this back into a plan view, looking down on the top of our structure. And now I'm going to select the additional 2 quadrants here to begin modeling our lifting lugs. And I can choose the visibility by selected objects. So now you'll notice that my manhole in that quadrant is completely hidden. And we will start off by adjusting our drawing grid. So currently it's kind of down through the middle here. Let's just change this orientation here so that instead the user-defined drawing grid is now through the horizontal direction. I'm going to take this top node and I'm going to use the Move Copy tool. I'm going to make one copy about the user-defined coordinate system here, U, V, and W, and I'd like to move it negative 12 inches in the V direction. Let's set this to 0. I always double check to make sure that all of these settings are cleared out, so I'm not making any copied lines or surfaces between the nodes. And now similarly, we have just a node kind of floating up above the tank surface. So just like what we saw with the manhole, I'm going to select a line over on the left. I'm going to hold down my control key to select the top node. I continue holding my control key to drag and drop and make a copy of a vertical line passing right through the top of that surface. And once again, I'm going to access the Connect to Lines or Members. I hover over this location and the program will place that node directly where the line intersects the surface. I am now done with the top line. I can just delete the single node at the top as well as the bottom, and we're left only with that intersecting node here. I'd like to take this node and I'm going to use the Move Copy tool to create one copy in the U direction here of 4.8 inches above the top of my roof surface. So I click OK. We've just simply made a copy here. Now the purpose of this node up here is to define where we want the opening for the eye of the lifting lug. And in order to define the eye, I want to draw a new circle. And I just want to draw the circle as a line element. So we go up here to our line element, and in addition to straight lines and arcs, we also have the ability to define a circle with a radius. So I choose this option. I just simply snap on that center point. I can type on my keyboard the size of the radius as 0.5 inches. I hit enter on my keyboard, and now we have our first circle shown. I want to do the exact same thing with the outer circle, but this time the radius will be 1 inch. I hit enter on my keyboard. Okay, so you'll notice that I have some nodes generated here automatically from this circle, and it's a little bit difficult for you guys to tell, but these nodes are actually green. And that's in contrast to all of the nodes that we've been using so far, which are a sort of maroon color. Well, the reason for this, if I double click on one of these nodes, it's not the node type standard. You'll notice everything's grayed out, and that's because it's generated from that circular line. So if we want to make changes, we'll have to kind of extract that node away from this line, which we'll see in just a minute. But what we can do with this is to use our Move Copy tool still with it, and we create one copy. The displacement vector here is going to be -8, -2, and 0. I click OK. So I just kind of have a node floating on the inside of my tank down here. And I want to create a line element that connects this node up to this outer circle. And I do so with a straight line element. I connect from the first point here and I zoom in, and instead of choosing this exterior point, I actually want the tangent point. And you'll notice that the program snaps directly to that tangent. And I can click on that, right click to exit. Now, the tangent point is controlled by object snap. So again, similar to AutoCAD, we can take a look at the object snap settings clear down at the bottom of the screen, where I can right click to edit the object snap. Take a look at this second tab here, and this is where we can turn on and off the ability for perpendicular, parallel, tangent, maybe quarter points, third points. Everything is available to us here for those object snap settings. I'm going to take this line and utilize the mirror tool. Before I do, let me zoom out just a little bit because I want you to see those user-defined coordinate system down here at the bottom. So I use the mirror tool. I'm going to create a copy, and this time I want to mirror about the UW plane. So we change this to the user-defined and we choose UW. The mirroring point is going to be the center of my lifting lug. I click OK, and so now we just have the line mirrored about the other side. I am going to use this Connect Lines tool, and I'm going to hover over all of these elements I just created. What this is going to do is to break apart all of those line segments where we have other lines intersecting it. So this allows me to then click on some of these nodes that we don't need, and just to simply clean up the model a little bit, I can zoom in here and clean up this additional node. So now we have a significant portion of the lifting lug drawn. I want one more straight line at the bottom of the lifting lug here to kind of close that loop. Now, currently, these are all just lines and nodes. We don't have a surface defined, so there is no stiffness, material thickness associated with this lifting lug. How we do that is to draw a new surface, and within my drop-down box here, I can just simply select the boundary lines. I choose stainless steel. We already have that defined. The thickness is going to be set to 0.75 inches. I click OK. I simply snap on this exterior line. The program recognizes it's a closed loop, and my surface is automatically generated. Now we do want to add an opening here for the eyelet of the lifting lug. In the similar way, right next to drawing a surface, I can draw an opening, and I can simply select the boundary lines here to consider that opening. So our lifting lug on the left-hand side is complete. Now I'd like to copy this over to the right-hand side. So what I can do is just to use my selection box here to only select the lifting lug. I can use my mirror. I want to create a copy about the UW plane again, and my reference point is going to be right here in the center at 0070. I click OK, and now my lifting lug is drawn to the other side. But we have one slight problem that we need to take care of, is that these lifting lugs are now passing through the top of this surface. So similar to the manhole, what I can do, and I think it's a little bit easier if we turn this into a wireframe view, to select all these surfaces that kind of have this intersection going on, we can right click, and under surface, we can choose the option create intersection. So now you can see when I go back to the rendered view, the program automatically recognizes where this lifting lug is connecting to this somewhat complex curved surface at the top of our domed roof. Now I want to do the same thing over here, and let me exit out of this. We'll turn this to wireframe view, and we select our lifting lug and some of these component surfaces that are associated here. And we right click on the surface, we choose the option to create intersection, and once again, we have a nice visibility here of where those are passing through each other. I want to hold down my control key here to select both of the components underneath the tank to right click and deactivate. So now those surfaces really no longer exist for our analysis. And essentially, once I cancel out of this visibility mode, the bulk majority of our modeling is complete with the tank, including the manhole and the lifting lugs. So what we would like to move on to now is the legs. And of course, this tank is going to be sitting on some type of legs along with eventually the foundation. So to move on to the legs, I do have a node existing underneath these axes here. And if I would like to disable the view of these axes, that's all controlled under the display tab. So this display tab really allows me to turn on and off everything graphically here that I'm viewing. This will come into handy as well once we view our results. But for these axes at the 0 point, what I can do here is essentially scroll down to where I see the general tree. And from here, I have the axis system where I can disable the X, Y, and Z at the 0 point. So now I can see this node that was somewhat hidden underneath there. I'm going to take this node, and we can also access our Move Copy tool by just right-clicking on an element. So we don't necessarily have to go up to this toolbar every time, but another way to access it is to right-click, choose Move Copy. We create one copy. We want it about the user-defined coordinate system here, and we will copy it 0017 inches in the W direction. Underneath the expanded settings, I want to create a line element between my copied nodes. So now when I click OK through all these dialog boxes, we have a simple line element shown 17 inches away from that original node. I'd like to draw a rigid support surface here for the bottom of my leg. And the purpose of this rigid support will make a little bit more sense further on, but it's really just for load distribution down into our support. So in order to draw this 2-inch by 2-inch rigid support or rigid surface, I'm going to change around my drawing grid here, and we're still in the user-defined drawing grid. So I can also relocate my origin of the drawing grid by snapping to this node here. So now you can see that my drawing grid is on that same level. If I zoom out, all of these tiny little points here on my drawing grid by default are set at 1 foot, and that's a little bit too big for our example today. So we can edit that by right-clicking at our drawing grid options down at the very bottom of the screen. So I right-click, I choose Edit, and instead of the default 12 inches, we can modify this to every 1-inch spacing. When I click OK, you'll notice my drawing grid is significantly smaller, but now all of these little points are located only 1 inch away from each other. So to draw my rigid rectangular surface, I can use my drop-down box up at the top to choose rectangle, but even better would be the rectangle via center. I want to change the stiffness type here to rigid. So this is a very high stiffness. Notice that I can't define the thickness or material when we choose this option. It's really used only for load distribution. I click OK, and I snap to that node that I had copied over, and I can just simply choose a point 1 inch away, and now you can see my 2-inch by 2-inch plate was automatically created here. Turning this into a wireframe view with my view options up at the top, I'm going to hold down my control key to select all 3 of my exterior lines here. Now, previously, yes, we're familiar with the Move Copy tool. We could create surfaces between the copied lines, but also what we have the ability to do, just another option within the program, is to right-click to extrude the line into a surface. So with this option gives me the ability to define first the material. We'll just choose the material we've been working with, the stainless steel. The height is going to be 21 inches. The thickness of my legs I set at 0.12 inches. Then I choose the global positive Z orientation, which we can see that available in our axes located down here in the lower left. I hit apply. I can right click to exit these. Maybe we turn this into a rendered view. And now we can see those legs extending up into the body of the tank. Now I'd also like these legs to taper. So as we move closer to the body of the tank where we're holding a little bit more weight, maybe we want to make these legs a little bit wider. So I'm going to go back to a wireframe view. I'm going to hold down my control key here to select my top 2 nodes. I'm going to use my rotate tool, and we are going to set this to 5 degrees, rotate it about our user-defined coordinate system here and the V-axis. And we want to rotate based on one of these bottom points of our legs. I want to make sure I have off all of these settings here just to clear out if any copied lines or surfaces between nodes or lines. I click OK, and now you notice we have a nice taper for our legs here as well. So going back into the rendered view, let's take a look at the base of these legs. So I put this rigid plate in here because eventually I want to get support reactions for my foundation design, and I'd really just like X, Y, and Z components. And I can do so by just adding a simple nodal support right at this location. So all forces that are coming down from these leg surfaces will be concentrated to a single nodal support at this point here because of that rigid plate. So again, that's why I said we should use the rigid plate for load distribution only. Well, I'd like to create a new nodal support, which I can do so here. and I create a new definition type. Of course, we have the ability to specify in any of the 6 degrees of freedom, 3 in translation, 3 in rotation, whether the support is fully fixed or fully released. We have partial fixity here with spring constants, and because RFEM is a nonlinear analysis program, we can specify geometric nonlinearities here as well. So if we have a friction support, sliding, maybe we have failure in uplift, for example, all of that is possible with these nonlinearities. Now for today, I want to specify just a typical pin type support, but here's the issue, that my nodal support reactions are going to be based on these global X, Y, and Z coordinates. But in reality, I'd like to orient these supports so that they're facing towards the center of this circular tank structure. So this is just going to save me a little bit of time later on, so I'm not having to work with the geometry here to find out what my rotated X, Y, and Z reactions are for my foundation design. So how do we slightly rotate this support? Well, we can use this option here to rotate the axis system. And I go under my detail settings here, and I can specify the specific angle about the X, Y, and Z axis I'd like to rotate, but better yet, we have the ability down here at the bottom to reference another object in the model. And for this example today, I can graphically select this line. If you remember, we created a little while ago, line number 49. So when I click OK through all of these dialog boxes, and I click here on the nodal support where my rigid plate exists, you'll see that this support is actually rotated towards that center node there of my tank, rather than being rotated based on these X, Y, and Z axes. But it's also very clear that right now our support is upside down. And that's just simply because if I right click on this line to view the local axes, remember the support is referencing this line, well, my Z axis is pointed downwards. So how do we quickly change that? No problem, just double click on the line element itself, go to the rotation. We can rotate 180 degrees. I click OK, and now you can see that our support is in the correct position here. So I can right click, turn off the local axis system. What I would like to do is to rotate these legs around the rest of my structure without having to remodel everything manually. So let's turn this into a wireframe view, and I'm going to highlight only over this leg and this nodal support, and also hold down my control key to select this line. I'm going to use my rotate copy tool. I want to make 2 copies here, and I want to rotate 120 degrees. We want to rotate about the global Z axis this time. That's fine. We could use either the global or the user defined. We'll choose the Z. We want to rotate about this 0, 0, 0 point. I make sure again that all of my settings are turned off here. Yes, they are. I click OK. And just like that, we have our additional legs modeled. But if I turn this into a plan view, and I take a look at my model, that original support is great. It's facing towards the interior center point of this tank, but these other 2 are not. And that's just simply because these other 2 supports are still referencing that original line. So in order to address this, let's go back to an isometric view. And we can simply zoom in here, double click on a support to edit it, create a new support definition type. We choose the user-defined axis system, and all we need to do here is to select the new line element that is relevant to that particular support. So line number 73. I click OK, so now we're referencing this line here, number 73. I do the same thing for my third support. I create a new definition type. I'm going to choose the user-defined axis system. I can graphically down here choose same as line and select this line in the rear, which is line number 58. I click OK, click OK. Let's turn this back to a plan view, and now you can see that all supports are oriented facing the center of this tank. One more thing to take care of though, if you remember, we go back to this render view, these legs are just passing up through the body. So this probably tells us we need to do some type of intersection tool again within the bottom legs for the body of the tank. I can do this by actually highlighting all of my elements here at once, really. And I can right click, and under surface, I can choose the option to create intersection. Program thinks a little bit, I can zoom in, and automatically I have all of the points here that the program internally places a line where these surfaces intersect. I can turn this to a wireframe view, and then I have the ability here, which if I kind of change around my viewpoint, I want to hold down my control key to select all of these internal surfaces from my legs on the inside of the tank. I right click, I deactivate the component, and just like that, they will no longer be taken into consideration with the analysis. So we're only considering these lower surfaces here. All of the internal surfaces, although the lines and nodes are still shown, are not there anymore for the analysis. That really sums up the modeling here of our tank. And there are a couple more points that we need to discuss before we get into loading. And the first is going to be the FE mesh. So I'm going to turn off my grid setting down here at the bottom. And let's go up to calculate FE mesh settings. The default FE mesh settings for a new model is typically 12 inches, 1 foot. So if I choose the option here to regenerate my FE mesh and I click OK, we can take a look at our FE mesh generated. And maybe I turn this into wireframe view and we can see that this is an absolute disaster. This FE mesh is entirely too large to get accurate results here. Going back to the rendered view, and actually one more thing that I forgot that I wanted to put at the top of this manhole cover is a rigid surface, but we'll get into that in just a minute. We can see here that with our manhole cover, you know, the FE mesh just really is too large. We're getting one FE mesh across the height of this. If we look at our legs, this is probably the worst. We definitely don't want to see FE mesh that looks like this. So what this tells me is that we need to significantly refine this FE mesh. So before we do, let me just quickly add in a rigid cover to the top of this manhole. And I can do so by just selecting a new surface type by selecting the boundary lines. It will be the stiffness type of rigid, no problem. I click OK, I snap to the top of this manhole cover, and I just wanted to place that rigid cover. The reason why is because when I go to calculate generate FE mesh, I think the terrible FE mesh is even more apparent when we look at this rigid cover. It was circular, but because the FE mesh is so large, the program can only see 4 FE mesh points, so it now creates a square type manhole cover here. So under calculate FE mesh settings, what we can do is to refine this FE mesh to something more like 2 inches. I regenerate the FE mesh, I click OK. The program thinks for just a second. We can see that this looks significantly better. We now have a circular manhole here. You know, the body of the tank looks much better. There are still some areas though that we'd like to refine this FE mesh. Now, the benefit of adding FE mesh refinements is that we can decrease the size of the FE mesh for a more accurate analysis, but we don't need to decrease all areas of the model. The more FE mesh elements we add, the longer the calculation time, where it may not really impact our results too much. So we have these special FE mesh refinement features shown in the program. What I'm going to do is that rigid surface I'm using for the manhole cover, let me go ahead and hide that by choosing the option visibility by hiding selected objects. Remember this line element we created way back when, which that's what the pipe is currently referencing for its geometry. I can right click on this line and I'm actually just going to create a node on the line by a specific distance. I'm going to choose 25% from the line end, so just simply 2 inches. I click OK. I now have an extra little node shown here. I can right click on this node to add an FE mesh refinement. I create a new refinement type. The program has grayed out everything except for the options for a node because it recognizes, okay, you want to add an FE mesh refinement to the node only. We'll keep this as circular. We define the radius as 12 inches here. The target inner length is going to be 0.3 inches. The outer length will be 0.7 inches, and I click OK. When I click OK out of this dialog box, you'll notice that we now have this FE mesh refinement symbol shown everywhere as a 12-inch radius symbol. And so everywhere within this 12-inch radius, we're going to refine that FE mesh. Now we can graphically see this by going to Calculate, Generate FE mesh. So we have an even smaller FE mesh all around this manhole. It transitions quite nicely right back into the 2-inch global settings. In a similar manner, we want to do the exact same thing for these lifting lugs. So if I hold down my control key to select both of these center nodes, I right click to add in a new FE mesh refinement. I create a new mesh refinement type. This time I give it a smaller radius of 8 inches, but the target inner length is 0.1 inches. The outer will keep at 0.7. I click OK. The program will go ahead and apply these FE mesh refinements here. I go to Calculate, Generate FE mesh, and now I can zoom in to my lifting lugs to see that the FE mesh looks considerably better. Now this is very important for accurate results. Our legs, we still have an issue down here as well. Right now, for a single surface, we have only one FE mesh element across that entire width. It's really recommended that you maybe have 3 or 4 FE mesh elements across that width. So what we can do is to highlight all of our legs here, right click to edit the component, because remember these components are part of this intersection. And I have the FE mesh tab here. I can activate an FE mesh refinement. We give it a target FE length of 0.3 inches. I click OK. The FE mesh refinement symbol is going to be shown as this little flag down here. So that's what is being displayed for my surface FE mesh refinement. I go to Calculate, Generate FE mesh. And now we can see that this FE mesh looks considerably better. It transitions quite nicely, again, back to that 2-inch length set for our global settings. Now, these FE mesh refinement symbols under the Display tab all the way up at the top, we can always turn them off. So they're still occurring in the background, but maybe they're just kind of getting in our way when we're modeling. We can just simply turn them on or off with this option up at the top. The next thing to discuss before moving on to loading, which is incredibly important, is local axes. So each surface element, if I right click and turn on the local axes system, has of course its own X, Y, and Z axes. Now, these X, Y, and Z axes should be oriented in the same direction for all surfaces, and there's a couple reasons for that. The first is for loading purposes. So when we're going through and we're loading these surfaces based on their local axes, you can imagine it's going to be somewhat of a disaster if we try and load multiple surfaces at once based on their local axes, and the axes are kind of oriented in every which way. We're not going to get a uniform load for what we hope. The other, and maybe I guess you could argue more important reason, is that our results will not be interpreted correctly. All of the results, which we'll see in webinar 2, for surfaces such as internal forces are based on the local axes. So you can imagine that if this surface here was oriented with the y-axis vertical, this one was with the y-axis horizontal, our results would not make much sense when we're trying to graphically view them and how these internal forces are flowing from one surface to the other. So what can we do here to kind of make sure that we clean up the model and to orient all these axes the same? The first thing I can do is go to my Views tab. And the Views tab allows me to turn on and off surfaces, for example, by their thickness. So what I can do here is to choose all of my 0.2-inch thick surfaces. Maybe I choose also my 0.4 for my manhole, and I choose my 0.75 for my lifting lugs here. I can highlight all of these surfaces. I can right click to edit, and we have the Axes tab. The Axes tab allows me to rotate all of these surfaces, local x-axes, for example, parallel to a line that I can choose within the model. Now this line is completely arbitrary, but if I want to align all my x-axes according to this vertical line here, I click OK. I click OK. And now we'll see that all x-axes should be facing in the upward direction for all these surfaces visible here. In the same exact manner, maybe I want to activate my 0.12 inch thick surfaces, which these would be my legs. So I'm going to highlight all of the leg surfaces. I'm not highlighting any of the components up at the top that are maybe deactivated, just really the active surfaces here. I right click to edit the component, and we're going to orient the local x-axis parallel to any arbitrary vertical line here. Line number 82 is great. I click OK, and we can cancel out of our visibility mode here to see that all local x-axes oriented in the same direction. So that takes care of X and Y, but Z is a little bit different. With the Z axis, you can see that for the body of my tank, it's pointing inward, and my legs is pointing outward. Again, very important for loading purposes, which we'll actually see in just a minute. Under the Display tab, I have the ability at the very bottom to view my colors in the graphics according to, let's say, the surface stiffness. You know, remember we have a rigid surface up here. Maybe I want to view according to the surface thickness. And now the colors are based on the different thicknesses. But we also have the option to show the plus and minus Z sides of the surfaces. So when I go into a solid display of the model, all of the red surfaces have my Z negative pointing out toward me, essentially. We see the blue surfaces down here. That would just indicate the positive Z axis is pointing outward. So you can imagine that this would be extremely beneficial for a huge model that you just want to quickly look. If one of these surfaces within the body, if I right click and I reverse the local axis system, was entirely blue, we know that our Z axis is not oriented in the same direction. Well, what I'd like to do is to point all of these Z surfaces out. So I go back to my Views tab here. I'm going to select all of my 0.2. We're also going to select the 0.4 inch surfaces. I can highlight, let me actually right click to turn this local axis system back to where it originally was. We highlight all of these elements here. I right click, and under the surface option, I have the ability here to reverse the local axis system. Everything's blue. I deactivate my view here, and now all local Z axes are pointed out. We do have this rigid surface here. I guess technically we could reverse the orientation for that, but I'm not so concerned with loading the rigid surface or results, so not so important. So definitely something that you want to pay careful attention to before you get into loading. All right, so right-clicking, turning off the local axis system. Maybe we want to go back to the display here according to the surface thickness, and we'll go back to a rendered view. Let's get into loading options. And I can create a new load case here up in my Quick Tools. The first load case is just going to be self-weight. So we can title this one self-weight. The action category here is going to be set to dead. Action categories are important because these reference the ASCE 7, and it's going to put the correct load factors in front of the applicable load cases. So we leave this as dead. We leave self-weight activated here, -1 in the Z direction. All densities will essentially be considered for self-weight of all the materials defined within our model. The next load case I define is going to be the fill load. The action category here might be something like live load. Notice self-weight is unchecked. We don't want to count for it twice, and we create our third and final simple load for today, which will be wind with the action category of wind. Now, in reality, for a true project, of course, we're going to have many more load cases, many more fill load cases, probably several wind load cases. So under the actions category, this would be where we have the ability for wind loads, for example, to define if they're acting simultaneously, alternatively. Because of our simple application today, that's why all of these options are grayed out. The combination expressions. The program will automatically generate the LRFD load combinations for us and the ASD load combinations. If I'm just curious to see what these are based on the standard, I can click this little info button here. Now, same concept for the NBC standard, for example. You would see both your ultimate and serviceability load combinations generated. The load combinations tab is going to list out all of the load combinations individually. So I'm going to see here my LRFD load combinations in orange, my ASD in red, based only on those load cases that I've defined. Keep in mind that with load combinations, the default method of analysis is second order. So we will consider both big P delta and little p delta. This is in contrast to load cases, which is run according to a geometrically linear analysis. This has to be done in order to combine it into load combinations and run according to a second order analysis. Now, finally, we have the result combinations tab. This is just an envelope solution. So we're going to compile all of our LRFD load combinations together, and my second result combination will be all my ASD load combinations. When we run this particular result combination in the model, you'll see here it'll just be an envelope solution, meaning we'll show the max and mins for all the results, considering deformations, internal forces, support reactions. So it's somewhat of a summary of all these load combinations. When I click OK, we can see now in our drop-down box, we've now set up the load cases and combinations, but we need to actually apply the loads to the structure. So for self-weight, I'm not going to add any additional loads. Rather, we're going to move on to the fill load. And the fill load is quite interesting when we have complex geometries like this. So what I'd like to do is to view this model in the reverse X direction here. And I'm going to take this top node and hold down my control key and select the bottom node as well, and use my move copy tool, which we're very familiar with. What I'd like to do here is to move it in the global X, Y, and Z directions, 24 inches in Y and 0 in X and Z. I make sure, again, all of my information is cleared out from our previous options. And now we can see these two nodes generated over on the right-hand side. I want to make a mirror copy of these nodes. So I create a copy. I'm going to mirror about the XZ plane, and I'm going to choose any center point here, 0, 0, 0. I click OK. So now I have 4 points on either side of the structure. Now this will make a little bit more sense in just a minute, but I'm going to select all 4 of these nodes, and currently they're all sitting at different X coordinates. If I double click them while they're all selected, I can change the X coordinate to 0 all at once. So now these nodes are just sitting right at the center of my tank. So in order to apply this fill load, we're going to use what's called a free rectangular load, and I can access it here within my dropdown, and I choose new free rectangular load. I'm going to apply this to only the surfaces here within the body of the tank. So I go to my Views tab, I select here maybe only my 0.2 thick surfaces. I'm going to highlight only essentially the bottom of the tank and the walls. I click OK. The fill load is going to be oriented according to the local z-axis of the surfaces. So again, this is why it's very important for those local axes. If the z-axis was different for each surface, it's very difficult to apply a load all at once. We want this to actually be in the YZ plane. So we can reference these. It's kind of into the plane. And we want it to vary in the Z direction. What I mean by this is at the top of my fill load, I don't want any load. That should be 0. But as we decrease down the height of this tank, I really want to see a load at the bottom of 0.4 kips per square foot to account for the weight of that fill inside. Now I'm going to select my 2 points to apply this free rectangular load. So I cancel out of this visibility, and this was the whole purpose here of creating those strange exterior points. But now you can see when I click OK that I now will consider the fill load on the inside of this tank for all the surfaces that I selected. And even more so, it's going to vary linearly from 0 kips per square foot down to 0.4 kips per square foot. And in webinar 2, this will make a little bit more sense once we can actually look at the load distribution. So of course, for additional fill loads, maybe we'd want to account for friction in the vertical direction and have several more load cases. For the wind load, again, a simple application for today with free rectangular loads again. I want to take these nodes, hold down my control key, highlight all of them, and use my move copy tool. I'm going to create one copy, and I'm going to set this as 7 inches in my vertical direction here of Z. I click OK. So now you can see all I'm really doing is just setting the main points here that define the bottom of the tank, where the walls start and end, as well as the top of the tank. So for the first wind load, we go to a new free rectangular load. And I want to apply this here only to my surfaces at the for the walls. So not the bottom or the top, but just the walls themselves. This will be in the projected X direction. So into the page, the projected direction will allow us to take into consideration the curvature of the tank. It will be uniform, and the magnitude here is going to be negative 0.011 kips per square foot. I then choose my points here that only define those wall elements. I click OK, and now we can see a nice windward and leeward wall, load acting on these walls here. For the top of my roof, I would like to essentially emulate a type of suction force that maybe we've calculated from the ASCE 7. So for this, I go back once again to a new free rectangular load. This time though, I want to select only my top surfaces. So I'm going to create a visibility here of just those 0.2 inch thick surfaces, and I select from left to right. I'm really not paying any attention to the manhole surface or the lifting lugs. We could include those if we wanted to as well, but just considering only the suction surface on the main body of the tank here, I click OK. We want this to be acting in the local Z direction. So according to each surface's local Z-axis, we want it to vary linearly in the Z direction. So at the top of the tank, I want a suction force of 0.026 kips per square feet. And at the bottom, I want something significantly smaller at 0.009 kips per square feet. I select my 2 points by canceling out of this visibility. I choose my top upper left point, my lower right point. I click OK, and now internally, which if I even turn this to a wireframe view, we have this suction force acting on all of those top surfaces. And finally, in a very similar manner, we want a pressure acting on the underside of the surface. So we once again go to a new free rectangular load. We want this to be acting only on the bottom. So I reactivate my view here of the 0.2 inch thick surfaces. I click OK. This will be a uniform load acting on the local Z axis with a magnitude of negative 0.021 kips per square foot. I choose my 2 points by deactivating my current visibility mode. I select my upper left down to my lower right. I click OK, and now we have this pressure acting on the underside. So we can cycle through to view these various load combinations with all of our loads applied to the structure. Now, I know that you're all probably just dying to see an analysis. We've spent so much time on modeling, but unfortunately, you will have to wait until the next upcoming webinar, part 2. We will plan to hold this within the next few weeks in February, so we will post it on our website fairly soon, as well as send out the reminder email. But this essentially will show the analysis results in RFEM from all of our modeling and loading that we did today. I want to address singularities and how we can combat these. I want to discuss stability and buckling considerations, because that is a true concern for thin steel surfaces that maybe not all programs are able to take a look at. We will touch on the RFEM add-on modules for design as well. So you can register on our website. Like I said, we'll be posting that soon, but as most of you know today, we send out a couple reminder emails before that webinar will take place. So keep an eye out for that within the next few weeks. So to sum up today's webinar, please visit our website at dlubal.com to learn more information about RFEM, all of the add-on modules that we have. This also includes our web shop, which all of our pricing information is shown there. I always encourage everyone to follow us on our social media accounts, specifically maybe YouTube, which has all of these videos and previously recorded webinars similar to this posted that you can watch at your own leisure. Facebook, LinkedIn, Twitter is going to announce all of the events and conferences that we'll be at, maybe new technical articles that we've written, frequently asked questions. If you have any questions or comments about today's presentation or anything else, feel free to email us at info-us@dlubal.com. And our phone number here in our Philadelphia office is 267-702-2815. So as I mentioned, we will have plenty more upcoming webinars, in particular the second portion of this plate modeling webinar sometime in the next few weeks in February. You can register on our website or register directly through email. Many of you are wanting PDH certificates. These will automatically be emailed to all participants who are here for the 60-minute duration. So that 60-minute duration is required by the states which we are pre-approved to provide PDH certificates to. So if you were here for the 60 minutes, you can expect to get that within the next day or so. If there was anybody who watched the webinar and you did not register for the webinar yourself, but rather you watched with a colleague or whatever else the situation may be, can you please request a PDH at the email address shown here at info-us@dlubal.com. So again, if you personally did not register for the webinar with your own email address and your own name, and you are wanting PDH for today, please request that at the email address shown here, info-us@dlubal.com. And with that said, I want to thank everyone for attending today. And as always, we hope to see you at our next webinar. Thank you.